Hello, class. Welcome to the first part of Chapter 1. Today we'll be going over just a few parts of Chapter 1, and then we will do the rest tomorrow. The first thing I want to talk about is something that's core and integral to your understanding of what we're going to be going through. And I think it's best explained with a simulation. So if we go take a look here, this is a little simulator that I found. And what it does is it simulates tossing coins. And you'll notice right here, there is a scale from 0 to 1, which is representative of the probability of something happening. So 0, and here's 1. So if I were to toss the coin just once, you'll notice that I currently have a 100% rate of getting heads. Because, I flipped it once and it was heads. If I did this again, all of a sudden it jumps down to 50% because the first one was heads, the second one was tails, and that makes 50%. Now it's 33.33% tails or 66.7% heads. And if I actually keep going, you'll notice that it's kind of dancing around a particular number. In fact, the particular number is 50%. Let's say I do this a few more times. This is taking a little longer, so let me crank this up to like 200. And if I did this for 200 times, you'll notice it's kind of dancing all around that 50% mark. In fact, if I turn this thing on right here, I can actually see that line. I can see that I get really close to it. And this actually holds true even if I get some kind of weird coin that has a different probability. Like maybe I make it, say, 25%, right? Let's just reset this. If I were to do 200 trials at 25%, over a long enough period of time, it would actually get closer and closer to that 25% mark. It's going to kind of dance all around it. Obviously, we expect some degree of variation. That's not surprising to anybody, but it's still very, very, very close. What I'm illustrating here is this thing called the law of large numbers. The law of large numbers is as the number of independent trials increases, the long run relative frequency of repeated events gets closer and closer to some value. Let me say that a little less mathy. As we do random stuff over and over again, eventually the true probability comes out. This is actually pretty cool because what it allows us to do is to take a look at things that maybe don't seem random, like the recovery rate of an illness or the success of a particular program. And over a long period of time, we can actually come up with a percentage that can show us the probability of whatever thing succeeding or not succeeding. Now, before I can move on, I do need to talk about something that I don't like. And you guys know, I have a lot of things that I don't particularly like, but this is another thing. We need to talk about, well, here, let me give you guys an example. Let's pretend that you go to job interview after job interview after job interview, and you keep getting turned down. People just keep saying no to you for whatever reason. If someone says to you, "Hey, man, the next one's bound to be good because you had all these bad ones," that's good intentions, but that's wrong. And I'm gonna tell you why that's wrong. It's wrong because the universe owes you nothing. The universe doesn't owe you anything. It doesn't matter if you've been turned down from 10 jobs. The universe doesn't owe you a job. That's not how things work. If you keep getting bad grades, you're not suddenly due for a good grade. If you are trying to shoot a free throw, just because you miss like 30 of them doesn't mean that you're magically going to make the next 10. The universe owes you nothing. That's not how things work. And yet, people will frequently talk about this. Here's some examples of this kind of logic, right? If I toss a coin 10 times, the first 5 tosses are heads. I'm not somehow magically guaranteed that the next 5 tosses are tails. They could be, but if they are, it's not because the previous 5 were heads. If you're a 90% student, you're not suddenly guaranteed a 100% if you've failed a bunch of previous exams. If a baseball player expects to be at bat 10 times in a game, he's not due for a hit if he's missed every pitch previous. This kind of faulty logic is called the law of averages, and it's not real. It's fake. And you'll hear people quote this kind of logic all the time. They'll say something like, "Oh, it's we've had a drought. We're due for some rain soon." No, the universe owes you nothing. They might say something like, "I don't know, you know, this is actually the logic that people use that are gambling addicts, right? It's like, man, I keep losing this to blackjack. I'm due for a win. I'm due for a win. I can feel it." No, the universe owes you nothing. Here's a couple questions that I want you guys to answer on screen, and then after you answer them, I'm going to go over them. A particular disease has a recovery rate of 96%. How is something like this figured out? The way that that is figured out is we take a look at the long-term relative frequency of people that have recovered from a case, and we're like, hey, 100 people have had this thing, and 96 of them recovered. Our current, best estimate is that there's a 96% success rate of recovering. That's what it means. It's just we can look at the long-term um, uh, way something is played out, and then we can tell it from there. Here's another one. You're walking down a street with a friend. You were sad because you just asked someone out and they said no. In fact, this is the 8th person in a row that you have asked out and they have said no. Your friend says, "Cheer up. The next one's bound to say yes." Comment on your friend's logic. Well, your friend is certainly well-meaning, but unfortunately, no. If 8 people have said no to you, that does not guarantee you the next one is a sure thing. Hopefully, we're praying, we're hoping for you, but not a guarantee. So now we need to shift gears and we need to talk about probability. There's two kinds of probability. There's empirical probability and there's theoretical probability. Empirical probability is actually what we've been talking about. It's this just kind of observed probability. That question with the recovering from a disease one, that's just based off of an empirical probability. It's just what we've seen. Theoretical is based off things that we can actually predict, like dice rolls or coin flips, or pulling cards out of a deck. Those are the three kind of classic staples of probability. That's what we call theoretical. So before we can really dive into this, I need to do a bit of a vocab dump. We need to talk about some things. One event of a random phenomena is called a trial. So if I roll a dice, that's a trial. If I flip a coin, that's a trial. What happens on that trial is what we call an outcome. So if I roll the dice and I get a 6, the outcome of my trial is 6. And a collection of outcomes, we call that a sample space. We're going to get into that in a second. The next slide's all about sample spaces. And last thing is when we combine a bunch of outcomes, we can sometimes call that an event. It's important to note the word trial and the word trial and outcome are very frequently. I'm babbling here. The word trial and the word event are very frequently interchangeable. Trial and event are interchangeable. So let's talk about sample spaces. I have 4 examples of sample spaces here that I kind of want to just quick go through. So you notice for the first one, if I just roll a dice, I have the S symbolizing sample space. It is equal to, I have those weird squiggly brackets. Those are called set brackets. And I've listed all of the possible outcomes. I can get a 1, 2, blah, 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 or a 6. Those are all the possibilities. We were talking about the different denominations of cards. We have like 1, which we call aces, 2, 3, 4, all the way up to 9, 10, jack, queen, king. It's important to note that if you have a particularly long string of outcomes, there's nothing wrong with just putting dot, 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 as long as the pattern holds. There's nothing wrong with that. If we talk about the suits of cards, again, S is equal to heart, diamond, spade, club. They don't have to actually be numbers, it's just what the outcome is. This last one bears a bit of explanation. Rolling a dice 3 times and recording the number of odd numbers. Well, if I roll a dice 3 times, it's possible I don't get any odd numbers, hence the 0. I could get 1, I could get 2, or I could get 3. It's important to make a distinction. This top one and this bottom one are very different in one very key component. In the top one, we would call all of these outcomes equally likely. I'm just as likely to get a 6 as I am to get a 1. In this case, they are not equally likely. The probability of getting a 0 is not the same as getting a 1 or a 2. Because they're different, that means that they are not equally likely and aren't useful for constructing a probability. But we might be able to figure that out later. Here's some basics of probability. P of A just means like A is just the event. So it could be rolling a 6, or rolling an even number, or tossing a coin and getting a heads. That's the number of outcomes in A. And the bottom part is the number of possible equally likely outcomes. For example, rolling a 6, getting a 4 on a 6-sided dice, there's a 1 out of 6 chance of that happening. So we will write that 1 out of 6. Picking a boy from our class, we have 4 gentlemen in our class. That's 4 over 12, which reduces down to 1/3. Yes, you should always reduce your probabilities if you're going to leave them in a fraction form, or if you just want to write a decimal or a percentage, all those are fine as well. There's some other ways that we can actually model probability. For example, if I were to ask you to roll 2 dice and model that probability, we understand that the numbers could be from 2 to 12, but it's a lot easier when you look at it in this way. When we look at it in this way, we can actually see how often the particular outcomes occur. For example, the probability of getting a 12 is 1 out of 36. There is one instance of 12, and there are 36 different outcomes. You'll notice 7, which is highlighted in red, is actually the most likely number for you to roll. In fact, you have a 1 out of 6 chance of getting a 7 if you roll 2 dice and add their numbers together. Question 1. Create a sample space of all the possibilities of tossing 2 coins. Please ignore the rolling. Just tossing 2 coins. What are all the possibilities of that? You should have something that looks like this. The sample space, they could be both heads, could be heads, tails, tails, heads, and tails, tails. It's possible that you got this wrong because you only wrote heads, tails, or head, tails, or tails, heads, but it's important to note that those are different events. They happen differently. Let's keep going. Based on your sample space, what is the probability that you get the same outcome on both tosses? If you said 50% or 1/2, you are correct. That's right. If we look back here, I can just see, well, how many of these have the same outcome? This one does, and this one does. That's 2 of them. There are 4 total outcomes. 2 out of 4. You guessed it, 50%. The next one. Let's extend this to 3 tosses this time. Make a sample space for 3 tosses. And here's a hint. There should be 8 possible outcomes. Keep that in mind when you guys give it a try. Here we go. These are the options. Heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Tails, heads, heads. So on and so forth. I'm not going to say all those. You guys get the idea, though. These are all the different possible combinations of getting heads and tails when I toss 3 coins. Alright, let's do another one. What's the probability, based on what we just saw, that you get at least 2 heads? So I toss 3 coins. What's the probability that I get at least 2 heads? Oh, look at that. Again, 50%. It's like a coin toss. Let's go back and take a look. At least 2 heads. Let's count those events. There's 1. 3 is at least 2. 2, 3, 4. And the rest only have 1 or none. So that's 4 out of 8. And again, if I put that into a fraction and figure that out, it's going to be a big old 50%. Your homework is a record-breaking low number of 10 problems. You guys are to do this, and tomorrow we will go over it. I don't think these are terribly difficult, but do the absolute best that you can.